This is the curve whose slope is its own height. Last lesson we hunted it down. Now watch what happens when we hold a mirror up to it. The mirror lies along the diagonal, where the across and the up are equal. Reflect the curve in it, and a different shape comes back. Flat where the first was steep, steep where the first was flat. That new curve has a name. It is the natural logarithm. Reflecting in the diagonal is what an inverse does. It swaps the two coordinates. The point at across 1, up 2.718, is now at across 2.718, up 1. So the logarithm undoes the exponential. Hand it a height, and it gives back the power that produced it. This curve paid for a lot of history. From the first tables in 1614 until calculators arrived, hard multiplications in navigation and astronomy were done by looking numbers up and adding. And we already owe it a number. Last lesson, the slope of doubling settled on 0.693. We named it and moved on. Today we find the slope of this curve, and here is the promise. No algebra at all. We are going to read the answer off the mirror. Because a mirror does one very specific thing to a slope, and that one thing is the whole lesson. So, what does a mirror do to a slope? Take any point on any curve, and take one small step along it. The step has an across part and an up part. The slope is the up divided by the across. This step goes 2 across and 1 up, so the slope is 1/2. Now reflect the step. The mirror swaps across and up, so a step that went 2 across and 1 up now goes 1 across and 2 up. The two parts have traded places, and the division turns over with them. The reflected slope is 2. Whatever the slope was, the reflected slope is 1 divided by it. You can see it with no arithmetic at all. Shallow reflects into steep, and steep reflects into shallow. And the diagonal is its own reflection, because 1 divided by 1 is 1. That is the only slope the mirror leaves alone. One case needs care. A flat step has no up at all, so reflecting it gives a vertical line, and 1 divided by 0 is not a number. But the curve we are about to reflect never flattens. Its slope is its height, and its height is never 0, so the reciprocal always exists. That is the entire tool. Reflect a point in the diagonal, and the slope there turns upside down. Now put the tool to work. Pick any point on the exponential. Last lesson handed us its slope for free. The slope of this curve at any point is its height at that point. Cornering, that was the whole of lesson 11. Reflect the point across the diagonal. It lands on the logarithm. And by the rule we just proved, the slope of the logarithm there is 1 divided by the slope we started with. 1 divided by that height. Now look hard at where the reflected point actually sits. When the mirror swapped the coordinates, the old height became the new across. So 1 divided by the old height is 1 divided by the new across. The slope of the natural logarithm is 1 divided by how far along you are. 1 over x, and look at what is not in it. There is no logarithm left anywhere. Read it off 3 times. At across 1, slope 1. At across 2.718, slope 0.368. At across 7.389, slope 0.135. Each one is the upside-down copy of a slope on the other curve. Plot all those readings and you get a curve you have known for years. The hyperbola, 1 over x. That was a picture argument, so check it against a measurement, the way lesson 2 would. Take the logarithm at across 2, step forward 1,000th, and see how much the height changes. The reading is 0.499875. 1 divided by 2 is 0.5. The measurement is climbing onto it. Now read the shape off the formula, because 1 over x tells you everything this curve does. It is positive everywhere the logarithm exists, so the curve always climbs. It never turns over. But it shrinks. At across 10 the slope is 1/10. At across 100, 100th. Still climbing and climbing almost flat. And yet it never stops. There is no ceiling it settles under. Go far enough and it passes any height you name. Far enough is very far. To reach a height of 100, you go out to about 2.7 times 10 to the 43. At the other end, it does the opposite. Approaching 0, the slope explodes, so the curve dives and never quite reaches the vertical axis. One thing to notice on the way past, because a later lesson runs it backwards. If the slope of the logarithm is 1 over x, then accumulating 1 over x gives back a logarithm. Now the number we owe, 0.693, the slope of doubling at the start. Doubling can be written using our base instead. 2 is our base raised to some power, and that power is exactly the natural logarithm of 2. So 2 to the x is our base raised to x times that number. A function inside a function, so the chain rule from lesson 7. The slope is that number times the curve itself. At the start the height is 1, so the slope at the start is the number alone, 0.693147. That is the reading from the first minute of last lesson. A number nobody chose, and now it has a source. Which raises the obvious question, what about logarithms to other bases? The same mirror answers all of them. Reflect tripling and you get the logarithm to base 3. Reflect 10 to the x and you get the one on your calculator. Every exponential slope is its own height times one fixed number belonging to its base. So every one of these logarithms has slope 1 over x, divided by that same number. For base 10, it is 2.303, so the slope is 1 over x divided by 2.303. A constant hangs off the answer. Except for ours. Its fixed number is 1, so nothing hangs off anything, and the slope is exactly 1 over x. That is what the word natural means in the name. Two quick runs, because in an exam what you need is speed. The slope of the logarithm of 3x, a function tucked inside another, so the chain rule from lesson 7. Outer rate 1 over 3xx, inner rate 3. The 3's cancel, and the answer is 1 over x. The 3 vanished, and that is worth a second look. The logarithm of 3x is the logarithm of 3 plus the logarithm of x. A fixed number added on lifts the curve and changes no slope. Now x times the logarithm of x, two things multiplied, so the product rule from lesson 8. 1 times the logarithm of xx plus xx1 over xx tidies to the logarithm of x, x1. Two traps. The first is a mismatch. The logarithm only exists for positive numbers, but 1 over x is perfectly happy on the negative side. The repair is an absolute value around the inside, and it is the most dropped symbol in this topic. The second trap is the log law run backwards. The logarithm of a sum is not the sum of the logarithms. 2 and 8 make 10. But the logarithm of 2 plus the logarithm of 8 is the logarithm of 16, nowhere near the logarithm of 10. Notice what we never did. No difference quotient, no limit. We took a curve we already understood, held a mirror to it, and read the answer off the reflection. 1 reflection, 1 reciprocal, 1 over x. Next lesson, a curve you cannot rearrange to get the height on its own, and how to differentiate it anyway.